Merci, Muriel, and bonjour, everybody. Well, it's my great pleasure to introduce you into the field of internal corrosion and some interactions between mechanical loading, stresses, and internal corrosion. Well, I've been working in the topic since 1994, so first at the University of Siegen, where I did my PhD. Well, then I was for postdoc at the University of Pennsylvania. Then I spent 12 years as a professor at the University of Applied Sciences, Osnabrück, some time at Chalmers University of Technology. And since 2018, I'm at the Steel Institute and was they're responsible for the materials engineering of metals. Well, of course, I have to acknowledge a lot of financial support that was given us to study so this concept. Well, let me shortly introduce Aachen University and Aachen. So Aachen is located at the triple point between the Netherlands, Belgium, and Germany. Well, it has become famous since the Romans because of their hot springs that can be found in the surrounding, and it was also the residence of Charlemagne, so a very important European who built this beautiful cathedral in the year 800. Well, and then we have Aachen University. It's one of the Germany's large technical universities. So we have a turnover of about 1 billion euro per year, and we belong to the Germany's University of Excellence. Well, so the university had grown, and that is the Aachen city center, and it became larger and larger. So we have an outward campus, and it spread from Aachen city center to the Netherlands border. Well, here you find that is the Steel Institute, and we have two further locations. The Center of Metallic Design, where we do the testing, or servotronic testing, and then here we have a research center for digital photonic processing, means additive manufacturing. Mining and metallurgy, that was a nucleus 150 years ago, and in 1910 the Steel Institute was founded by famous Professor Fritz Wüst. So after him the iron oxide, the wüstite, was named. In 1945, it was unfortunately completely destroyed during World War II. That is how it looks like today. And so we are about 110 employees, and our research covers the complete value chain of engineering alloys, from the casting, forging, additive manufacturing, analytics, and testing in simulation and experiment. And that covers also internal corrosion issues. And let me just explain what is internal oxidation. Internal oxidation occurs in a binary alloy where the oxygen partial pressure is not sufficient to oxidize the substrate, but the alloying element B. And then oxygen diffuses into the alloy, B diffuses outwards, and then we get internal B oxides. Essentially, a similar situation is given if both oxides are higher than the, so that's a wrong way, so the higher than the oxygen partial pressure, then means then A oxide is formed. So that must be just the other way around, sorry for that. Then the superficial A oxide is formed, and then the further growth is then governed by the oxygen and A diffusion. But at the same time, we have the situation that at the interface between A oxide and the alloy, the oxygen partial pressure is still sufficient to form internal B oxide, and that is then shown here. Again, driven by O diffusion, oxygen diffusion, and B outward diffusion. Well, here we have an example. So that is a nickel 10 chromium alloy. Here we see the formation of nickel oxide wall. That is a fast growing oxide. And while at the same time we have situation was the internal oxidation of chromia. Well, of course, was then due to the consumption of nickel during the process, was the part of the internal oxidation soon then will be inside so the nickel oxide. Well, but if we increase, so probably all of you know it. Well, if we increase the chromium concentration to 20%, then we have then the B diffusion, the outward B diffusion is much higher, and then we get a superficial scale instead of internal oxidation. And that is basically the concept of selective and protective oxidation, and the minimum concentration can be predicted according to so the famous Carl Wagner theory of internal oxidation, whereas then CB dot is then the minimum concentration for the transition from internal to external oxidation. Okay, internal nitridation is essentially the same. So we have the situation, and sorry, that must be the other way around. If the equilibrium partial pressure of B nitride is higher than the nitrogen, lower, than the nitrogen partial pressure, then we will get the formation of internal B nitrides. Well, the nitrogen diffuse inwards and then forms also B nitrides. And again, here you can see that is an example of a nickel chromium aluminum titanium alloy, and also here you see the internal nitridation attack. And once we apply a tensile load on this situation, then we see the brittle cracking within this near surface layer. And if we have a closer look, then that is due to the complete coverage of the grain boundaries by internal nitrides. Well, both internal oxidation and nitridation can be described by Carl Wagner's theory of internal oxidation. And here's the solution of the diffusion differential equation for oxygen diffusion and for the B diffusion in an alloy AB. So these two solutions can be coupled by a mass balance at the precipitation front. That means the flux of oxygen coming to the diffusion to the precipitation front and B, that must be essentially the same with respect to the stoichiometric coefficient. And when assuming a parabolic progress of the internal precipitation zone, and the condition so that the B diffusion is much slower than the oxygen diffusion, then we come to this very simple equation for the progress of the internal oxidation or nitridation front. Well, I will give you two examples to illustrate. So this equation, that is the internal nitridation of in nickel 20 chromium and X titanium. While chromium itself is not nitrided under this condition, but so depending on the initial titanium concentration, so if the initial titanium concentration increases, then we have a decreasing internal nitridation depth. And that is according to this simple equation. And if we increase the solubility, that means more nitrogen, then we get a higher internal nitridation depth, as it's shown here, because with adding chromium, we increase the solubility for nitrogen. Well, then we have, well, of course, well, then the nitrogen diffusivity that plays a role in this equation. Well, however, well, the Wagner approach is an oversimplification because it does not consider, well, thermodynamics and the effect of mechanical stresses. And here I would like to give you an example. Once more, here we have internal nitridation, and so driven by nitrogen inward diffusion. But well, so when we carry out X-ray diffraction measurements of the residual stresses, then we see, well, so it's about 370 megapascal in compressive stresses, and so these compressive stresses are then due to the higher specific volume of the nitrides as compared to the substrate. And so this higher specific volume causes what an outward diffusion of the substrate metal atoms. That can be then seen, well, so that forms so this kind of substrate metal protrusions at the surface. Well, the mechanism then we assume, well, that is either Nabarro-Herring creep or dislocation pipe diffusion. And in fact, by the TM, you can see, well, an increased, well, dislocation density in the precipitation area. Well, if we have a more quantitative look on it, then we can see, well, here we have internal nitridation at what different temperatures, and so the higher the temperature, so the deeper the internal nitridation attack, and so the higher is then the surface coverage by these protrusions, by this substrate metal protrusions. So that is what, if we quantify it, then the surface covering what corresponds nicely what to the precipitation depths of internal nitridation. Well, so to account for this kind of effect, so we tried to solve so the Wagner or the underlying equations, so the diffusion equations by means of or numerically by means of finite differences. While here was the differentials of Fick's second law are then just replaced by difference quotients. And basically, that means that that we have three concentrations at a time step t, and using these three concentrations, so we can calculate the concentration of the following time step, and by so this difference equation. That is pretty simple, but so we have to consider the precipitation process. That means, well, so the thermodynamics. So what we are doing, so we have implemented the Calvert here in terms of using the ChemApp. Can also use thermocalcs. That's pretty much the same. And then we take this calculated concentration and we correct it according to thermodynamic equilibrium. And then we have these new concentrations, and then we can calculate the concentration as the next step. And that allows us to predict internal corrosion also of precipitates of moderate stability. That's an example of chromium nitride, as you can see here, where we have some kind of a diffuse precipitation front. Well, more recently, we have been using the method of cellular automata, where we use the probabilities of particle movement in spatial directions, so to the top, to the bottom, ballistic or in diffusion direction. And by doing this, then we can, can see then we have so the diffusion of nitrogen and so the counter diffusion of titanium, and also here, so in green yellow, you can see that is then the ongoing precipitation, and so that allows us to predict then the precipitation depth. So the advantage using this is that we can consider the various transport passes and stresses and so on. Well, in most technical applications, so we observe both oxidation and nitridation simultaneously, and often failure of a protective scale leads to internal attack. Well, here are two examples from technical failure cases. Well, first, that is a broken natural gas burner, and here we had a large crack, and then this complete burner was then broken and not working anymore. And when we had a look on these cracks, so we found a massive internal nitridation attack by 0.5 millimeter. And so obviously, the chromia scale was not able to protect this material. And the second, then a furnace bolt that is probably due to overheating, and then we can see massive internal oxidation, intergranular oxidation attack by internal chromia and internal oxidation by silicon. Well, if you go back to the schematics, then we have situation. So we have the A oxide and internal oxidation of B oxide, but at the same time we have a high nitrogen partial pressure. So that, for instance, it's a situation that we just have in air. Well, if then a mechanical load is then superimposed, then the oxide may crack, and then so there's access for the nitrogen, and then there's a risk of then deep internal nitridation attack. Well, here's an example of an artificial crack that we introduced by a diamond saw cut, and basically we had a 100 hour of oxidation, so formation of a chromia scale. Then we applied the saw cut, and then that was then followed by a 100 hour nitridation experiment. And as you can see, so we have an increase in the titanium nitridation attack, and that is supported by the simulation result as well. That is then shown by a two-dimensional finite difference simulation. Well, obviously, chromia is permeable to nitrogen. It does not protect to nitridation, and that is manifested by the next example, where we found a complex corrosion pocket. So that is opened up by means of focused ion beam sectioning. While here we have locally a chromia scale in the vicinity of an chromium carbide, and then we get the carbide is then transformed to chromium nitride. We also get aluminum nitrides, and the formation of carbon. And there's the idea that we get a reaction with the carbon, with the hydrogen from the atmosphere, and then a very high pressure increase that opens up to this kind of porosity. Here you see this in 3D. That is the complete corrosion pocket, and that is this pore formation. Well, so ladies and gentlemen, an obvious or an exceptional combination of high temperature and stresses can be found at gas turbine plates in gas turbines. And so these loading, so we try to simulate by means of thermal cycling, TGA. Well, that is something I think Daniel will report on later on, so therefore I want to focus on that. And while by creep testing, while here we did creep testing in a pure nitrogen atmosphere, which means then so this glass cylinder is then fed by hydrogen, and so immediately at the sample, so we place a package of titanium sponge in order to reduce the oxygen partial pressure and really to focus on internal nitridation. Well, let's have first a look on isothermal oxidation of CMSX4. That is a single crystalline material used for gas turbine blades. And as you can see here, although we have a smooth alumina scale, but if we change the situation, so from isothermal wall to thermal cyclic exposure, which means every 5 hours the sample was then cooled down, and we were using this kind of a wedge-shaped sample, which means with a sharp tip. And if we have a look on the sharp tip under these cyclic oxidation conditions, then we see then we can see a massive degradation of the material behavior. If you have a closer look, then we see, if you have a closer look here, then we see that thermal cycling causes to repeated alumina spallation that ends up in a near surface aluminum depletion. And so this aluminum depletion causes a transition to non-protective nickel oxide formation, fast growing, as you can see, so we call this a cauliflower that is this fast growing nickel oxide, and this then, so the internal oxidation and nitridation is then in combination with massive internal stresses and crack formation. Well, when we want to simulate these such conditions, so we have to take into account that so the diffusivity is then increased by the superimposing creep stress, and that is then shown here. That is an experiment under a pure nitrogen atmosphere. Here we have the situation with of the sample where we do not have high stresses, so nearly 0 megapascals, and if we apply then 30 megapascals, then we have a decrease by almost 100% in the internal nitridation depth. That means that is essential to take the creep stresses into account. Sorry. Well, finally, I would like to address the influence of diffusion paths with a focus on grain boundary diffusion. Well, so we know that the lower the temperature, so the higher the influence of grain boundary diffusion. While here we have an example that is alloy 718. That's typically used for gas turbine discs, and at 1000 centigrade, so we see a rather homogeneous internal oxidation front, which means internal oxidation within the bulk is the same than along the grain boundaries, and at 850 centigrade, the situation is completely changed. So we have bulk internal oxidation, but a much deeper oxidation attack along the grain boundaries. That means at the moderate temperature, then so the faster grain boundary diffusion plays a major role. And at even lower temperatures and fatigue loading with superimposed dwell times, there is a risk of oxygen diffusion-driven intergranular fracture. That is a failure of such a gas turbine disk, and that was due to intergranular failure. That is then an example of an experiment, and then we see that the crack really follows the grain boundary. This is a fatigue crack propagation rate, which is just much higher. So then we observe under non-dwell time conditions. Also, the mechanism behind that is that we have a tensile stress acting on the grain boundary plane, and so that causes the diffusion or drives oxygen diffusion into the grain boundary, and so that lowers the cohesion of the grain boundary, and then finally intergranular cracking on a nanometer scale. While under vacuum conditions or without dwell time, so we have only cycle depending crack propagation, as it's shown here with the typical fatigue striations. Once we increase to dwell times, then we have an increase in the crack propagation rate by 2 orders of magnitude, which means 100 times faster crack propagation, and the fracture surface looks completely different. While here we see the non-deformed grain boundary facets. That is the influence of the dwell times. And if we have a closer look what's going on, then during the dwell time, so we have oxygen built up, and during the load reversal, then we observe the crack advance. So that is so once we know about this mechanism, so we can look deep inside and adjust the grain boundary structure. For instance, so we can apply grain boundary engineering type processing in order to improve the resistance of the material to this kind of damage. But so since so my 30 minutes are over, I would like to come to some conclusions. So I hope I could show you in which way internal corrosion is then driven by the diffusivity of the reacting species and thermodynamic stabilities. And it's strongly influenced by mechanical stresses. And so these mechanical stresses can be due to the geometry, for instance, at edges. So we have growth stresses of the oxide, or the difference in the coefficient of thermal expansion, also applied loads, which causes then cracking of the oxide, and then an increase in inward diffusion of the corrosive species like oxygen or nitrogen. If you have a closer look, then we have also intrinsic effects. So diffusion can be enhanced by diffusion along the interfaces. The diffusion can be driven by the occurrence of mechanical stresses to the higher volume of the internal precipitates, and then causes an increase in the dislocation density, and then an increase in dislocation pipe diffusion. So that is what we are right now try to implement in our numerical approaches, which gives us a bit more freedom than, for instance, the analytical model of internal oxidation as suggested by Karl Wagner in the late 50s. At the end, I would also like to mention that internal corrosion can also have a technical benefit. So we are using it then, for instance, nitridation and carburization of steel, while giving us a high strength surface. In a larger European project, we use internal oxidation as one method for oxide dispersive strengthening of these powder particles for additive manufacturing. And we can use it also for the surface treatment for hot dip galvanization of manganese steel, because hot dip galvanization of manganese oxide, so it's hardly possible. And therefore, what we are doing, so we do an oxidation treatment. Then we get an external iron oxide scale and internal manganese oxides, and then afterwards a reduction of the wüstite, and then we have a nice metallic surface that can be hot dip coated. Okay, well, and that brings me to the end. Thank you for listening, and if you have then later on further questions or contacts, and well, please free to contact me at any time. Thank you very much.